Okay, so this is a continuation of a prior video that we had made on the calculation of angular momentum of a flat plate, flat square plate. The plate is suspended about the point A, and it is rotating with a constant angular speed about the vertical z-axis given by capital Z. And while it is rotating about the vertical axis, it also has angular rotations theta in the xy plane. Now the way the coordinate systems have been described is that there are two coordinate systems. The point O is the center of mass, that is the center of the square, and there is a body fixed coordinate system xc, yc, zc. Xc and yc are along the or on the surface of the plate, and zc is perpendicular. There is another coordinate systems xy and z, small xy and z. That in that coordinate frame is such that small x and small y are along the edges of the square, and z is perpendicular to the surface of the square. So these two coordinate frames are parallel in the sense that they both have the same z. One is shifted with respect to the other, but the z coordinate is the same. Also the x and the y coordinates, the xc and the yc, are shifted from x and y. But we note that x and xc, y and yc, and z and zc are parallel to each other. So the requirement of this problem was to find an expression of the generalized expression of the angular momentum of this square flat plate as it is undergoing these rotations. So there are two rotations. One is the capital omega angular rotation, which is constant about the inertial z-axis, capital Z, and the other is the angular rotation theta dot, which is variable, and that is always perpendicular to the surface of the square flat plate. So here were the given the information that was given to us. We wanted to determine the angular momentum about the point A, and the angular velocity capital omega is constant. O is the center of mass or symmetry, so O is the center of the square. Now in this previous part of this problem, the way we approached the angular momentum calculation about the point A was that we first calculated the angular momentum about the point O, and then we shifted by looking at the angular momentum of the center of mass itself due to its velocity about the point A. So that's how we calculated the net angular momentum about A. So that is, and the advantage over there was that HO, because it was about the center of mass, did not use any moment, or rather the products of inertia. So the expression of HO was pretty simple. But on the other side, you had to have this, you had to compute this extra cross product to express the angular momentum about the point A. In this part, what we are going to do is we are going to directly calculate the angular momentum about the point A, and so in order to do that, so I'll keep the picture in view. We note that H at A can also be expressed as I omega. So I omega, I is the inertia tensor, and omega is the angular velocity. Now angular velocity, the net angular velocity of this square flat plate. So the expression, if you go over the basic expressions, is going to be Ixx omega x minus Ixy omega y minus Ixz omega z, and this is going to be in the IA direction. So let's say that my IA is along this x-axis, is the unit vector along this x-axis, okay, and then I will have I y y omega y minus I x y omega x minus I y z omega z, and this is going to be in the JA direction. So we are going to denote JA to be the unit vector along this y. So as you can see, we are directly expressing the angular momentum about the point A itself. Plus we will have I z z omega z minus I x z omega x minus I z y omega omega y. Yes, and this is Ka. Now we make a note that IA, JA and Ka are the unit vectors along x, y and z respectively. And we are talking about this x, this y and this z here. They are also body fixed. We note that x, y, z are body fixed with origin at A, right? So the xyz triad is not through the center of mass, and because it is not through the center of mass, we cannot assume that this product of inertia terms are zero. Hence we have to use the full expression. We also note that Ixy is equal to Iyx. These are standard results. Ixz is equal to Izx and Zy is equal to Iyz, just so that it is clear in case we flip the order of these alphabets when we express the products of inertia. Now the angular velocity that we need to use here is going to be omega A, and we are going to so these angular velocities are actually components of the angular velocities about angular velocity about A, omega y j A plus omega z Ka, and so these are the components along Ia, Ja and Ka. Now we note that x, y, z are parallel to x, c, y, c, z, c, right? So x, c's, and this is, I should say, respectively. And so x is parallel to xc, y is parallel to yc, and z is parallel to zc. So therefore we can just say that omega A is equal to omega c, because the unit vectors are parallel to each other, and so the expression for omega A is going to be, I'm not repeating the derivation of the angular velocity. If you go to the previous video, you will find the derivation of the angular velocity omega c here, and so I'm just going to take the expression. So I'll write the expression here. So omega A is then minus omega cosine 45 degrees minus theta Ia minus omega sine 45 degrees minus theta Ja plus theta dot Ka. So let me just put a demarcation here. Alright, so we have our angular velocities, angular velocity along the different directions. So all we need to do is substitute them and use the proper moments of inertia. So in order to get the right moments of inertia, we have to note that Ixx is going to be, Ixx is the moment of inertia of this square plate about this x-axis. So that is going to be Ixc, which is the moment of inertia along this axis, plus the parallel axis movement. Now the parallel axis movement is going to be by a distance L over 2. So you would have m L squared over 4. And so we had the moments of inertia identified in the previous part of this problem. So we had 1/12 ml squared in y and x and 1/6 ml squared in z. So we are going to do a parallel axis transformation. So you'll have 1/12 ml squared plus 1/4 ml squared. So that's going to give us 1/3 ml squared. Okay. And similarly, Iyy is also going to be Iyc plus ml squared by 4, and that is again because from yc to y it is a movement, parallel axis movement of L over 2, of distance L over 2. So you have ml squared over 4, so that will again give us 1/3 ml squared. Now Izz, the moment of inertia in the z direction, if we go back to this diagram, it is again a parallel axis movement of Izc, but now the distance moved is this half of the diagonal. Now since the square is of length L, its diagonal is square root 2L, so half of the diagonal is L over square root 2. So then you would have ml over square root 2 whole squared. So it's going to be 1/6 ml squared. 1/6 was the original, ml squared was the original about the center of mass, plus ml squared by 2. So this is going to be then 2/3 ml squared. Okay, so we have our moments of inertia, we have our angular velocity, and we need the products of inertia. Yeah, sure. So we need that. So let us consider Ixy. Ixy is going to be the Ixy about the center plus mass times x a with respect to O times y a with respect to O. So this is essentially this is a product of inertia calculation through parallel axis theorem. If the product of inertia about the center of mass is Ixyc, then about A it is going to be Ixyc plus m times the coordinate of A with respect to O. Okay, so what is the movement of A with respect to O times what is the movement of A with respect to O in the y direction. So in the x direction the movement is minus L over 2, that's this distance, and in the y direction the movement is minus L over 2. So then the net movement is going to be Ixyc plus m into negative L over 2 times negative L over 2. So that's now Ixyc is 0 because Ixyc is the product of inertia about the center of mass, and about the center of mass, if you take the axis of symmetry, which are these xc and yc, the products of inertia are 0. So you have ml squared over 4. Okay, going to Iyz, it is going to be Iyz with respect to the center plus m y of a with respect to o, z a with respect to o. So the y component of a with respect to o and the z component of a with respect to o. Now we note that the z component of a with respect to o is 0, and the product of inertia about the center of mass is 0. So therefore there is no product of inertia term in the IYZ direction. The reason this is 0 is that z and zc are parallel to each other, and they have so whatever is the z coordinate in the centroidal axis is going to be the same z coordinate in the axis about the point A. So they have the same elevation. So that's why there is no difference in the z, and so therefore this is 0. So you have the product of inertia IYZ equal to 0, and similarly xz is also equal to 0. We can verify it. Okay, so with that then we are able to put together the expression of the angular momentum. So let's write down the expression. So then h of a is equal to, so we are going to substitute Ixx is 1/3 ml squared times omega x. So omega x is minus capital omega cosine 45 minus theta, so we'll put a negative here, omega cosine 45 degrees minus theta, minus Ixy is ml squared over 4 times omega y. Omega y is minus omega sine 45 minus theta, so sine 45 minus theta, and we need to put the minus sign, so we'll have a plus here. So this is, and then and then we have Ixz minus Ixz omega z, but Ixz is equal to 0, so therefore we will not have this term showing up in our angular momentum expression. So this is in the IA direction. In the JA direction we have Iyy. Iyy is 1/3 ml squared, and this will be multiplied by omega y. Omega y is capital omega sine 45 degrees minus theta with a negative sign, so I'll bring the negative sign here, and then we will have minus ml squared over 4 times omega x. So omega x is minus omega sine 45 minus theta, so we are going to put a positive sign there. So let me just check. Oh sorry, this is cosine 45 minus theta. Right, so and then yz or Izy is equal to 0, so that part is not there, and then the last part is Izz omega z, and these two products of inertia are 0, so we just have to take this term. So the z moment of inertia is 2/3 ml squared, and that will be multiplied by the angular velocity in the Ka direction, so theta dot Ka, and that is the expression for the angular momentum. I mean, we can simplify this a little bit and write it as ml squared capital omega times negative 1/3 cosine 45 degree minus theta plus 1/4 sine 45 degrees minus theta, IA plus ml squared capital omega times negative 1/3 sine 45 degrees minus theta plus 1/4 cosine 45 degrees minus theta, that's JA, plus 2/3 ml squared theta dot KA. And you can double check this with the prior our prior calculations, and you should be able to verify that indeed our answers match. So let me just quickly check here. This is the angular momentum that was calculated by the previous method, and this is the angular momentum calculated by the current method directly through using A, and we see indeed that all the terms are matching. And here you see the unit vectors are IC, JC, KC, whereas here the unit vectors are IA, JA, KA. But that's not a problem, because as we mentioned, these two sets of unit vectors are parallel to each other. So therefore the components are going to be the same whether you express in the IA, JA, KA or IC, JC, KC. So this completes our problem. There is another part of the problem that can be done, and that is to find the rate of change of angular momentum. To find the rate of change of angular momentum, when we differentiate this, we have to also consider the fact that theta is changing, so theta dot terms will show up, but we also have to differentiate the unit vectors IA, JA and KA. Similarly, IC, JC and KC if we use this earlier expression. And IA dot, JA dot, KA dot are quite simple. They are basically going to be omega A cross IA, omega A cross JA and omega A cross KA. And we have already found the expressions for the angular velocity omega A. So that part is just a little bit of algebra. But this is then part 2 of the problem, where we essentially show how the angular momentum of this square disk with two different degrees of freedom or two different rotations can be calculated first with respect to the center of mass and then shifting it to A. And alternately, we can calculate directly with respect to A. With respect to A, the only issue is that we have to now consider the products of inertia, and we have to consider the parallel axis theorem to move the products of inertia as well as the moments of inertia from the centroid to the point A. So that introduces some extra calculations, the advantage with using the center of mass is that the moment of inertia of the center of mass is easier. It does not consist of any product of inertia terms, but then we have to move that moment of inertia, that angular momentum to the point A using that r cross mv term, which basically computes the angular momentum of the center of mass itself due to its velocity about the point A. So that introduces an extra term, but otherwise the two methods are equivalent, as we see here, and they give the same answer provided we use the same unit vectors or parallel unit vectors, which was the case in this problem. So that's it. Thank you so much.